Stretching 9 kilometers across the mouth of the eastern Scheldt, this barrier is anchored by 65 concrete pillars, rising 40 meters from the seabed. The project was a response to the 1953 flood, a disaster that claimed 1,836 lives and submerged 200,000 hectares of land. The original plan was simple: build a solid, permanent dam to wall off the North Sea. But local fishermen and environmental protesters fought the closure. They argued stopping the tide would kill the saltwater environment and end the region's oyster industries. In 1976, the government changed course, opting for a semi-open design. They installed 62 steel sluice gates that close only when the water rises dangerously high. This location is the final connection point between the North Sea and the inland estuary, positioned to act as a shield for Zealand. The design intended to provide total protection from storm surges, while allowing the estuary's saltwater ecosystem to function as if the barrier wasn't there. Decades after completion, it is becoming clear the estuary is no longer the same environment it was before the pillars were driven into the seabed. Even with raised gates, the mass of the concrete pillars creates a constriction, turning the structure into a semi-permeable filter. It alters the environment in 3 ways: stripping kinetic energy, blocking acoustic waves, and disrupting the movement of physical matter. Placing a massive 9-kilometer concrete structure across a tidal inlet changes the rules of survival for everything living inside. The most visible sign of this change is a geological process known as sand hunger. The pillars reduce the total volume of the tide and create friction. As the ocean water pushes past the concrete, it loses speed. Fast-moving water has the kinetic energy to carry sand from the sea into the estuary. When that water slows down at the barrier, it drops its load of sediment on the seabed outside before it can reach the interior. Inside the estuary, the natural cycle is broken. The existing sandbanks continue to gradually wash away with the outgoing tide, but the barrier prevents any new sand from coming in to replenish them. This loss directly impacts 100,000 wading birds, like the oystercatcher. As the sandbanks sink, the birds have less time to forage for mussels and cockles before the water covers their feeding grounds. By filtering out the ocean's kinetic energy, the barrier is eroding the physical foundation of the estuary's food web. The filtration effect extends underwater, where the barrier's physical design interacts with the sensory biology of the harbor porpoise. Porpoises navigate and hunt using high-frequency echolocation, sending out clicks and listening for the echoes to map the water around them. When the tide rushes through the gates, it creates intense turbulence. This churning motion generates dense clouds of underwater air bubbles lingering near the barrier. To a porpoise's sonar, these air bubbles act as reflectors. The sound waves bounce off the turbulence, making the open gate appear as a solid obstacle. In contrast, the harbor seal frequently crosses the barrier regardless of the current. Seals do not use echolocation. They rely on their vision and sensitive whiskers to detect water movement, allowing them to ignore the acoustic interference that stops the porpoises. An engineering project designed to allow wildlife passage has unintentionally created a sensory wall that filters species based on how they perceive the water. The barrier's role has recently expanded with the installation of tidal energy turbines inside the sluice gates. The addition of spinning blades in the gates raised a new question: whether these turbines would pose a physical danger to the animals that do cross. Measurements show the turbine's rotor axis is nearly 5 meters below the surface, leaving a 5-meter open water gap near the seabed. Harbor porpoises employ a behavioral safeguard, waiting for slack tide, the moment the water and turbine blades stop moving. Since 1986, the barrier has met its primary goal. It has successfully protected the coast from every major storm surge without failure. But the cost of the kinetic filter is a permanent need for maintenance. Ships must now move thousands of tons of artificial sand back onto the receding flats to stop the sandbanks from disappearing. The Eastern Scheldt shows that large-scale climate engineering is not a final solution, but the start of a perpetual negotiation with the natural world.